Okay, so well, last time you see we were looking at the statement that the set of holomorphic isomorphism classes of complex tori is in a natural bijection with the orbits of PSL2 with integer coefficients on the upper half plane, okay. And what we need to do next is to show that this set of orbits, namely U mod PSL2 Z, is actually a Riemann surface, and in fact the claim is that Riemann surface is just biholomorphic to the complex plane, okay. We need to prove that, and therefore first of all we need to see how the quotient U mod PSL2 Z even becomes a Riemann surface. So you see then of course it's another matter to prove that this Riemann surface is biholomorphic to C, that it is isomorphic to C, alright. So first of all we need to know how you need to know how you are able to get a Riemann surface structure on U mod PSL2 C, alright. So which means roughly the problem is like this. The problem is U itself is a Riemann surface, after all it is an open subset of the complex plane, so it is a Riemann surface. Any open subset of a Riemann surface is also naturally a Riemann surface, and PSL2Z is a group of holomorphic automorphisms of U, okay. Of course all possible automorphisms of U are Mobius transformations with real entries, alright, and then Mobius transformations with integer entries, if you take with elements of PSL2Z, they are also going to be automorphisms of U, and the problem is to go U mod PSL2Z. So the general problem is to take a Riemann surface and then to go modulo a certain subgroup of holomorphic automorphisms of that surface and to see where you can get a Riemann surface structure on the quotient, okay. Obviously you cannot expect this to happen for an arbitrary subgroup of holomorphic automorphisms, so it will happen for subgroups with certain special properties. So what one wants to do is to try to single out those properties. What are the crucial properties of a subgroup of holomorphic automorphisms of a Riemann surface, so that when you divide by the subgroup the quotient again becomes a Riemann surface, okay. So first of all let us look at, so what I am going to do is try to look at the situation for covering spaces, okay. That is I am going to look at the situation say for example even the universal cover, okay. If you take the universal covering space, then universal covering space modulo the deck transformation group is going to give you the space below, the space that this universal covering space is actually covering. So that is the starting point. So well, so recall, see if you have, so let me go back into for example even the topological category if you want, but of course whatever I am going to say will work also in the holomorphic category. So suppose X is a topological space, alright, then of course we are of course not working with arbitrary topological spaces, we are always working with topological spaces which are Hausdorff, arcwise connected, locally arcwise connected, locally simply connected, okay. So you take a topological space like that and then you have the universal covering, and you have this universal covering space, okay. This is something that we constructed, okay, and what we noticed here was two things. We noticed that if you fix a point X here and you fix a point above it X tilde, okay, and which means P maps X tilde to X, then we noticed that the fundamental group of the base based at the point small x can be naturally identified with the deck transformation group of P, okay, which is a subgroup of automorphisms of the universal covering space, okay. And well and we further also noticed that if you take this quotient is simply the universal covering modulo this group, namely the group of deck transformations. So in fact, so let me also write that x, if I write x to x sub univ to x, okay, and if I write x sub univ to x sub univ modulo deck of P, this is P, and if I call this map as this is a natural map, mind you the deck transformation group is a subgroup of automorphisms of the universal covering, and it is a group that acts on this, and this is just the orbits, the space of orbits, okay, and this is the natural map sending every point to its orbit under the action of this group. Then I told you that if you call this map as let us say Q, alright, then there is a natural identification of x with this in such a way that this it's so you can identify x with this set given the quotient topology, okay, namely the topology that makes Q into a continuous map, alright, and we have already seen this. Now one wants to look at a slightly more general situation, okay. So here is our first example, you have a space, you have this subgroup of automorphisms of the space, and then you are able to divide by that to get so that the quotient map becomes this universal covering, okay. Now more generally what can you do, okay. So well so it so happens that the reason you are able to divide by this group and get this as a nice covering has got to do with the way in which the deck transformation group acts on this, okay. So well, so let me make a definition, okay. So a group G of aught, let me take a topological space, let me call it as say Y, or let me even call it as W, okay. So W is a topological space, okay, and G is a subgroup of the automorphisms of W. Of course if I take W as a topological space, then these are all homeomorphisms, self homeomorphisms, and G is a subgroup of self homeomorphisms. I could also take W to be for example if you want a Riemann surface, and then the automorphisms that I am going to consider are going to be automatically holomorphic automorphisms, and G will be a subgroup of holomorphic automorphisms, okay. So really the argument does not depend on whether I am working in the topological category or in the holomorphic category, okay. So you take a group like this, such a group is said to act properly discontinuously on W. So this is the important notion, properly discontinuously on W if so maybe I should if for every small w in capital W, okay, there exists an open neighborhood U containing W such that G of U intersection U is non-empty implies G is equal to identity for all G in G. So see, please try to understand this definition. So you see if I try to draw a picture, the picture is like this. So here is my W, and you see, and I'm looking at elements of small g belonging to capital G. These are all automorphisms, okay, and certainly they are homeomorphisms. Okay. Now you take a point small w, okay, and take a neighborhood. Okay. If I apply G to this, okay, you can expect that I will get, obviously I will get W will be taken to G of W, and if this neighborhood is U, it will go to a neighborhood G of U. So G of U will be just a neighborhood of G of W, and of course you know G will induce it will induce a homeomorphism of U with G of U, because G is a homeomorphism, and homeomorphism restricted to an open set is going to give you a homeomorphism onto the image of that open set. Okay. So the question is, I mean the point is that when you, so what this G does is that it moves this neighborhood of W to a neighborhood of G dot W, and the condition is for each W I should find a neighborhood such that no matter what G I take, okay, that G should displace U completely away from itself. If I take a G different from the identity, of course if G is identity it is not going to do anything. If you take an element G, an element of the group which is not the identity, that is you take a non-trivial automorphism, then that automorphism, any non-trivial automorphism from your group has to move U completely away from itself, that is there should be no intersection between U and GU. So the condition is you must find such a neighborhood U that will work for every G, that is there is a neighborhood U of W which is pushed by every non-trivial element of G completely away from U, that is the condition. Okay. So this is the condition for properly discontinuous action. Okay. And well if you look at a covering space, then the deck transformation group does act in this way. So the first thing I want to say is that the moment if G acts properly discontinuously, then the first inference that one has to make is that G has no fixed points. Okay. Note that if G acts properly discontinuously, then G has no fixed points. So what I mean is then no element of G, then no element of G different from the identity, the identity element of capital G different from the identity element has a fixed point. This is obvious because you see if an element small g belonging to capital G has a fixed point, then that is going to be a point W such that G of W is equal to W. Okay. But you see W is in U, you take any neighborhood U, W is in U, G of W is in G of U, okay, but G of W is equal to W, therefore U and the G of U will intersect, certainly it will contain W, okay, and therefore if I take a neighborhood like this that cannot happen. Okay. So if it acts properly discontinuously, then G cannot have any fixed point. So in other words this definition of properly discontinuous is going to imply it's stronger than assuming that G has no fixed points. Okay. So in other words, so let me write that, in other words G acts without fixed points. There are no fixed points. So what is the standard example? If x tilde to x p is any covering, then the deck transformation group of that covering acts on x tilde properly discontinuously. Okay. if you take any covering, then you know the deck transformation group is a subgroup of automorphisms of the covering space, the space above, alright, and that will act properly discontinuously. This is just because of the presence of admissible neighbourhoods. See, because you know if I for a moment, you know, if I draw a diagram, so here is my x tilde, so here is my covering space, here is my P and here is my x. Suppose I have something like this. Well, given any, you know, give me a point here, let me call this as small x tilde, you know, then if you take its image here which is small x, okay, so small x tilde goes to small x, then this x has an admissible neighbourhood u, okay, so that is this u admissible neighbourhood of x. If you take this, then you know that if you take P inverse of u, the inverse image, it is a disjoint union of admissible neighbor, it is a disjoint union of open sets, okay, and each of which P maps homeomorphically onto u. So P inverse u is going to look like you know for every so P inverse u is going to be some u alpha, maybe I can use u tilde alpha, and well of course this is indexed by all possible x tildes where P of x tilde is equal to x, okay. So you take any point x tilde that lies above x, namely any point x tilde that goes to x under P, then there is then surrounding this point I have a neighbourhood u tilde sub x tilde which P will map homeomorphically onto this u, alright, and this will happen for every point. If I take some other point, okay, then I am going suppose I take a point y tilde, then I am going to end up with another I am going to just get u tilde sub y tilde, okay, and well P is going to map this u tilde sub y tilde homeomorphically onto u, alright, and now you see for the point x tilde, if I take this neighbourhood u sub x tilde, which is one of the pieces in the inverse image of an admissible neighbourhood of its image below of the, then this will satisfy the condition of this will give you the condition that you require for a properly discontinuous action. So you see so let me explain. So you see, suppose I take, so what is the deck transformation? So a deck transformation, G is an element of the deck transformation. So what does it mean? It means, you see, I have a map G is a homeomorphism of x tilde onto x tilde. Of course if I am in the holomorphic category, it is a holomorphic isomorphism such that it preserves the fibers of the covering. That means, you know, if I apply G and then apply the projection, I will still get back the projection. Of course another way of saying this is that G is a lift, it is a lift of P which is an automorphism of x tilde, okay, it is a lift of P, alright, and well you see the fact is that if I apply G to if I take a deck transformation and if I apply G to this neighbourhood, suppose I choose x tilde and I choose this neighbourhood, okay, then G dot that neighbourhood will not intersect this if G is not the identity, okay. So if G is not equal to identity, this identity transformation of x tilde, then you see G of u tilde sub x tilde, this neighbourhood, this will completely be different, this will not intersect u tilde sub x tilde, this will be nonset for, and this will hold for every G in deck in the deck transformation group. Of course G not equal to identity, okay, and that is obvious because you see G will move x tilde to, because G is going to preserve fibers, x tilde lies over x, so g of x tilde will be another point which will again lie over x, okay, and for that and g of u tilde of x tilde will be also a neighbourhood of that g of x tilde, alright, and that will also be mapped homeomorphically onto u, so it is in this inverse image, so it has to be but you know all these inverse images they are all disjoint, so therefore this cannot intersect, alright. So the moral of the story is that the deck transformation group, if you take any covering space, not necessarily the universal covering, take any covering space, you know of course universal covering is a special case when the space the space above is actually simply connected, okay, but you take simply any covering, then the deck transformation group is always going to act properly discontinuously, okay, fine. So this is a standard example of properly discontinuous action, alright. Now we come to trying to generalize the following, we go back to the situation. See, if you take the case of the universal covering, I am able to take the top space, I am able to divide by the deck transformation group, and I am able to get the covering, okay. So and of course mind you this deck transformation group is of course a fundamental group of this guy of the space x below, right. Now you can ask this question, take any covering space, okay, the deck transformation group of this cover acts properly discontinuously on the top space, can you divide by that and can you get back this cover, okay. So there is an obvious answer that you know if of course this will not always happen, okay, and there is an obvious restriction. For example, if I have to divide by this and get x, okay, then x should be the set of orbits of the deck transformation group on x tilde, okay, and that means that will mean in particular that the deck transformation group should act transitively on the fibers, okay. So that is already a restriction, you cannot expect to take any covering space like this, even though the deck transformation groups acts properly discontinuously on x tilde, you cannot expect x tilde modulo the deck transformation group to give x. So there is something slightly more that you have to assume, and this is where I mean this is the beginning point of Galois theory of coverings, okay. So you have to assume a special condition, namely the condition that the covering is Galois, okay. The other words that are used for that are normal cover or regular cover. So I'll make this definition a covering P from x tilde to x is called Galois or normal or regular, okay. These are other words that are often used. A covering is called Galois if given if for some x tilde belonging to x tilde, small x tilde in capital X tilde, and its image x equal to p of x in small x, you see I have the fundamental group of x tilde based at small x tilde, okay, and because you know the formation of the fundamental group is a covariant functor, what I will get is I will get a homomorphism, I will get a group homomorphism P lower star, okay, which is going to go from the fundamental group above to the fundamental group below, which is a very simple map. It just takes a loop above and then projects it down, you get a loop below, and then you do this mod FEP homotopy and you get this map, and it is a group homomorphism. So so what I want is, see this is a group, okay, when I take the image is only a subgroup, okay. So the condition is that the image should be a normal subgroup, okay. So let me complete this sentence, a covering P from x tilde to x is called Galois or normal or regular if for some point above and its image below the image of this is a normal subgroup of the target. So if I want to write it in symbols, so I will write P lower star pi 1 capital X tilde small x tilde is a normal subgroup of pi 1 capital X comma small x. So this is the condition. Okay. So normally we use this triangle symbol to normally we sometimes use a lesser than symbol to say it is a subgroup, and then we use a triangle symbol to say that it is a normal subgroup. Okay. So this is the condition. The condition is that the image of the fundamental group above in the fundamental group below is a normal subgroup. Then something nice happens. So once you have a Galois covering, then what happens is, so it's a very simple exercise to check that this group divided by this normal subgroup is going to give you a quotient group, and that quotient group is none other than the Dec transformation group. You see, look at the situation when this is a universal cover. When you have a universal cover, alright, then this is trivial. So its image is trivial subgroup, and trivial subgroup is of course a normal subgroup. The quotient is just this fundamental group below, and that is isomorphic to the Dec transformation group. So in this case also, so it's an exercise which is very easy exercise to do, is if P from X tilde to X is Galois, then the fundamental group below by the image of the fundamental group above, which is a normal subgroup, so I can divide by that. This is naturally isomorphic to the Dec transformation group. Okay. So the fundamental group below by the normal subgroup, which is the image of the fundamental group above, this quotient group is naturally isomorphic to the Dec transformation group. Okay. Now what is it? How does this definition help? This definition helps in the following, that in this case, that is, if you take a Galois cover and take the space above and divide it by the Dec transformation group above, then what you get is exactly the space below. So the fact is, the claim is if P from X tilde to X is Galois, then P may be identified. So I should write then X may be identified with X tilde modulo Dec P, and P with the quotient map X tilde to X tilde modulo Dec P. Okay. So the moral of the story is that if you have a Galois cover, you take the Dec transformation group above, then you divide by the Dec transformation group, what you get is a space below. This is a generalization of the case when if you take a universal cover, you take and you divide the universal covering space by the Dec transformation group, which is the fundamental group below, and you get the space below. So this is a more general case. Okay. So actually the Galois theory of covering spaces comes by studying these Galois covers. Okay. Well, so to prove this claim, let me state and prove a more general theorem. So So here is a theorem. Let W be you have to make some basic assumptions. So let us assume that it is it's a topological space which satisfies all our usual conditions, namely Hausdorff, arcwise connected, locally arcwise connected, locally simply connected. Let us put these blanket assumptions, though all of them may not be needed for the proof. Okay, so let G subgroup of automorphisms W act properly discontinuously on W. Okay, then the quotient map W Q to W mod G. Okay, so W mod G is set of orbits of G of in W. Okay, then this this quotient map is a Galois cover. It is a Galois covering with deck transformation group precisely G, with deck Q equal to G. Okay, so this is the more general theorem. Alright, this is the more general theorem. So if a group acts properly discontinuously on the space W, then the natural quotient map from W to W mod G is actually a Galois covering, and the deck transformation of this group of this covering is exactly G. Okay, so let us prove this theorem and also try to get this claim. This claim will follow as a corollary to this. Okay, so let us try to prove that theorem. It is pretty easy to prove. So you see, so I have proof. So you see my situation is, so I have the map W to W mod G, I have Q. Alright, now what I am going to do, if you look at the analogy of this covering space situation, the admissible neighborhood for a point below, okay, that is it's exactly one of its inverse images that gave you the open set that is required for verifying the condition of properly discontinuous action. Okay, so conversely, if you think, given any point, if you have that neighborhood which verifies the condition for a properly discontinuous action, then it's the image of that neighborhood below, you should expect that is going to be the admissible neighborhood of the point below, of the image of this point below. Okay, that is a natural way to think, and in fact that is the case. So first of all, well, W mod G is not even a topological space, so let us make it a topological space by giving the quotient topology. Okay, so make W mod G into a topological space by giving the quotient topology so that Q becomes continuous. Okay, so you know what the quotient topology is. A set in W mod G is open if and only if its inverse image under Q is an open subset of W. Okay, and therefore by definition the quotient topology is given in such a way that Q becomes a continuous map. Alright, so now at least this is a topological space and this is a continuous map. Now what one does is fix or even pick let W be a point, so this is Q of W be a point in W mod G. Okay, so small w is a point in capital W, okay, and I am taking its image here. If I take its image here I will get an equivalence class, okay, and I am calling it as bracket W maybe, and what is this bracket W? This bracket W is just the orbit of W under G, okay, so this bracket W is just G dot W, it is just the orbit of W under the action of G, alright. And of course I put this square bracket because in that orbit if I take some other element W prime and take its orbit I will get back the same orbit, so I can replace W by W prime inside this square bracket, okay, so it is an equivalence, two elements being in an orbit is an equivalence relation, okay, and it is not that equivalence relation that we are going, okay. So take this, now choose W, so there is, see, since G acts properly discontinuously on W, there is an open neighbourhood U of this point W which is completely displaced by every non-trivial element of G, alright. So choose U or let me say take U an open neighbourhood of W such that you know G of U intersection U is empty for all G in the deck transform in capital G with capital G minus identity, okay. So because we are given that the group capital G acts on capital W properly discontinuously given a point small w in capital W, there is this U such that GU intersection U is empty for G not equal to identity, alright, take that. And now consider G of U, sorry not G of U, Q of U which is a subset of W mod G. I am simply taking its image under Q, okay. Now the claim is that this is open and this is an admissible neighbourhood for this point Q of W. See if I take Q inverse of Q of U, if I calculate Q inverse of Q of U, okay, then what I will get is I will get all translates of U by elements of G, okay. So what I will get is this, I will just get various G dot U's or G of U's, okay, translates by G, okay, and this will be a disjoint union over G in G, this is what I will get. See if I have a point above, if I take its image below and if I take the inverse image, what I will get is I will get all translates of that point by the group, okay. This not only holds for a point, it holds for a set also. If I take a set above, that is a set in W, if I take its image Q of S and if I try to take inverse image, then I will simply get all translates of S by various elements of G. So I started with the U above, okay, I take its image below and if I now take the inverse image I will get all translates of U, but you see all these various translates of U they will not intersect U because for G different from identity I will get this disjoint union exactly one of this, namely for G equal to identity I will get U, for G not equal to identity I am going to get a G of U which is not going to intersect U, and mind you if you take G1 and G2 different, then G1 U and G2 U cannot intersect, okay, because if G1 U and G2 U intersect you can prove that G2 inverse G1 U will intersect U, okay. So this is actually a disjoint union, alright, and in any case since U is open, each GU is open, this is anyway a union of open set, so this is open, and this will tell you that Q of U is open because that is the quotient topology. A set below is open if and only if its inverse image is open above, alright. So Q of U is certainly an open neighbourhood, alright, and you see it is obvious that, see, from this there is another thing that this argument tells you. See, forget instead of U, if I had taken any other open neighbourhood, let us say I took an open neighbourhood V, if I push it down, take Q of V and then I take Q inverse Q of V, I will simply get union of translates of V by G. That is still going to be an open set, only thing is it may intersect. Because I took U, this was a disjoint union, but if instead of U I took some other open neighbourhood V, what I will get here is not a disjoint union, I will get a union of G of V, okay. So what it means is, in other words, it tells you that Q is an open map, okay. This also shows Q is an open map, okay. Q is an open map, and you see, now you see, if I take if I restrict that Q to G of U, then Q restricted to G of U will go exactly to QU, it will be a bijective continuous map which is also open, so it is a homeomorphism. Q restricted to G dot U, I mean G of U, from G of U to U is a homeomorphism, okay. So this will tell you that this open set U, maybe I should put this is not U, this should be Q of U, this is a homeomorphism. Therefore what it tells you is that this Q of U is an admissible neighbourhood for the point Q of small w. So let me rub this off so that I can write something more. Thus Q of U is an admissible neighbourhood for Q of W in W mod G, okay. So what has happened is that for every point you have found an admissible neighbourhood, therefore this is a covering space, okay. The only thing that I will have to check is that the deck transformation group of the covering is exactly G, okay, and I will also check that the deck transformation group is fundamental group below divided by image of the fundamental group above, that also can be checked, alright. So how will you prove that the deck transformation group is exactly G? It is very simple. So what you do is so let me do it here so that I have more space to write. So you see, so take the so let me fix some points. So I have Q W to W mod G, well I will fix this point W and then I will fix this point Q of W, okay. Now I will take the fundamental group at of the base at Q of W, okay, and from this I am going to define a homomorphism into the deck transformation group of Q, okay. I am going to define this. See So the first remark I want to make is that take any element small g belonging into capital G, any element by definition is going to be an automorphism of W, okay, which is going to respect the fibers of Q, because it is just going modulo G, okay. So what I am trying to say is so let me write that here. If you take, so here is my G, if this is an automorphism of W, and I claim that W, if I take Q to W mod G and if I put Q here, this diagram commutes. That is just because, you know, if I take a point x here and if it will go to the point G dot x, and x and G dot x are in the same orbit, so they will go to the same point below, because after all W mod G is just the set of orbits. Therefore by definition every element of G is a Dec transformation group. So you see, so this implies, you know, G is contained in the Dec transformation group, okay. G is contained in the Dec transformation group, that is very clear. Every element of G is automatically a Dec transformation by definition, okay. You will have, we would like to say that these are all the Dec transformations, okay. And well, if you go back and look at the way these Dec transformations were defined, okay. So how was this Dec transformation group defined? Well, you see what happened was, you know, there was this point Q of W, okay. If I take an element here, this is going to be a loop alpha, it is going to be homotopy class of a loop alpha at the point Q of W. And what is the Dec transformation that I define above? Well, you see, here is my W, I take the lift of alpha starting at small w, so I will get a unique lift alpha tilde, okay, and I take its end point, namely alpha tilde of 1. Now that is a point that is also going to lie over alpha, and you see since these two points, so you know, I want to make two remarks. So this map sends alpha to sigma of alpha, and what is the sigma of alpha? This is the unique, so let me put a belongs to symbol here, okay, this belongs to here. So this is the unique Dec transformation that takes W to alpha tilde of 1, okay. See, try to recall two Dec transformations, if they coincide at one point they coincide everywhere. That is because Dec transformations are lifts of the covering projection, and the covering projection has a unique lifting property. So to specify, if you want to nail down a Dec transformation, you have to just say it takes this point to that point, that is it. You cannot have more than one Dec transformation that carries a particular point to some other particular point, okay. So I take this unique Dec transformation which takes W to alpha tilde of 1, okay. And of course, you know, if I replace alpha by a homotopic loop, then you see this if alpha is replaced by a homotopic loop alpha prime, then the lift will also can be replaced by a homotopic loop, because the covering homotopy theorem says that you can lift homotopies, okay. Therefore it only depends on your alpha, the homotopy class of alpha, okay. So but you see, there is certainly a Dec transformation that carries W to alpha tilde of 1. What is it? See, since both of them go to the same point Q of W, they have to differ by a group element, by an element of by an element small g belonging to capital G, and therefore there is a small g which takes W to alpha tilde of 1. So that is going to be a Dec transformation that takes W to alpha tilde of 1, and that has to be this. So this has to be equal to the element small g belonging to G with G of W is equal to alpha tilde of 1. An element like this exists because these two are in the fiber over Q of W, which is the whole orbit, okay. So that it has to be that Dec transformation group, that element of the Dec transformation group. So the moral of the story is that, you know, the image of this is exactly G. The image of this is exactly G, alright. The image of this is exactly G, and what is in the kernel will be precisely those alphas which are liftable to alpha tildes such that alpha tilde of 1 is equal to W. Okay, so what is the kernel of this map? So the image of this, you can check that this is a group homomorphism, the image of this group homomorphism is precisely the Deck transformation group G by what I have told you, right. And the kernel, what is a kernel? Suppose alpha is in the kernel, that means alpha is liftable, alpha comes from a loop above, okay. But if alpha comes from a loop above, then this alpha tilde has to be a loop centered at based at W, that means alpha tilde of 1 has to be W, that means the Deck transformation has to be trivial. So the kernel of this is precisely image of the fundamental group above. So if you look at this, you can see that, you know, the fundamental group below based at Q of W divided by at least as a coset space Q lower star of the fundamental group above based at W is exactly isomorphic to G, okay. So of course you will have to do a little bit of calculation, and it is very easy to check that this is a normal subgroup, okay. It is a very simple calculation to check that this is a normal subgroup, you can check that. So this quotient group is actually G, okay, that which is exactly the Deck transformation group, okay. Yeah, and let me also add, take any Deck transformation, if I take its image under W, I am going to get some point, then I can join it by an alpha tilde and project that alpha tilde to an alpha, and that Deck transformation will be the image of this alpha. So you see this sigma is also a surjection onto Deck, okay, and Deck is Deck is exactly G, that is what I am trying to say. So here I just said that G is a sub of Deck, I am also trying to say that every element of Deck is also an element of G, okay. So let me again repeat it, you take an element of Deck, take W, that element of Deck will move W to some GW, okay, then I connect this by a path because after all its path is connected, then that path if I push it down I will get a path, I will get a loop below, and the Deck transformation induced by this map will be precisely the unique Deck transformation that takes this to that. So you see, so it is actually equality, this is actually equality, that is how you get this equality, okay. So the moral of the story is that whenever a group acts properly discontinuously on W, then W to W mod G is a Galois cover, Deck transformation group is exactly G, okay. Now the point I want to make is so this gives you a very clear picture about how you get quotients in this case, but let us look at the kind of quotient we are interested in. So let me also add one more thing. See, notice that the moment W is a Riemann surface, then because it is a covering, W mod G also becomes a Riemann surface, because after all this is you know, whenever you have a covering and if the base is a Riemann surface, then you can give a unique Riemann surface structure to the top, if the top is a Riemann surface you can give a Riemann surface structure to the base. So if W is a Riemann surface, then this also becomes a Riemann surface and this becomes a nice covering, okay. So the moral of the story is you take any Riemann surface, take a subgroup of holomorphic automorphism as a Riemann surface, okay, and assume that the subgroup acts properly discontinuously, then Riemann surface modulo that subgroup, that becomes the this natural quotient map becomes a holomorphic covering, and the Deck transform it becomes in fact a Galois covering, okay, it becomes a regular covering, Galois covering, and the Deck transformation group is actually this group G, that is acting, okay. So now you know how to divide by subgroup of holomorphic automorphisms which acts properly discontinuously, but there is still a problem, okay. Here what is happening is, notice that this definition of properly discontinuous action already supposes that G acts without fixed points, but that's not enough for our purposes. So you see, let me go back to what we are to the quotient problem that we are actually interested in. So the quotient problem that we are actually interested in is, you see, we are trying to look at U mod PSL2C. This is what we are trying to look at. This is the upper half plane, and PSL2C is Mobius transformations with integer entries, and we are trying to look at the orbits here, okay. And we are trying to, I mean, our claim is that this is a Riemann surface and this is biholomorphic to the complex plane, okay. So what is the problem in this case? See, first problem is PSL2 does not act without fixed points on U, okay. So you cannot apply this theorem. PSL2 does not act properly discontinuously in the sense of this theorem because it will have fixed points. See, for example, PSL2 has fixed points in U. See, for example, you know, it's very easy to write down, so you know, maybe I can take if I take Z going to, let us say, 2Z plus 1 by 2 by Z plus 1, something like this, okay. If I take this, then this is if I write it in matrix form, the matrix is 2 1 1 1, it is determinant is 2 minus 1 is 1, so it is an element of PSL2 and it has integer entries, so it is an element of PSL2C, okay. And what are its fixed points? Well, 2Z plus 1 by Z plus 1, if I equate to Z and solve it, I will end up with, well, I will get 2Z squared plus 1 is equal to Z squared plus Z, so I will end up with Z squared minus Z plus 1 equal to 0, okay, alright. And well, you know, I can maybe I can adjust these numbers, well, in any case this is a quadratic equation, okay. If I solve for it, I will get two, the coefficients are real, so I am going to get two complex numbers which are conjugate, one is going to lie in the upper half plane, the other is its conjugate is going to lie in the lower half plane, and these are going to be fixed points for this element of PSL2. So the moral of the story, so let me write this, roots are fixed points and one of them lies in U. In fact, you know, we have seen an automorphism of U is elliptic if and only if it fixes a point of U, okay. So these are elliptic elements, so PSL2 has elliptic elements, so there are fixed points, so it is not going to act properly discontinuously in that sense, because properly discontinuous action in that sense is that already it should act without fixed points. So what is the way out? The way out is we slightly relax this definition of properly discontinuous action and we give a slightly more general definition that is good enough to give us what we want. So let me propose that definition, okay. So let me write that out. So you see, I'm proposing this definition only for I'm going to propose this definition only for let's say subgroups of Mobius transformations acting on some open subset of the complex plane, okay. So definition, let G be a subgroup of Mobius transformations okay. We say G acts properly discontinuously at a point Z in C union infinity, okay. So you see when you are looking at Mobius transformations you should also include the point at infinity, okay. If you do not include the point at infinity then you are missing something, because a Mobius transformation can easily take a finite point to a point at infinity. So you have to look at the Riemann sphere actually, okay. So we say G acts properly discontinuous at a point if two conditions are required. The first condition is, see, compared with our earlier definition, in the earlier definition there were no fixed points, and there were not any fixed points means that stabilizers are all trivial, because after all stabilizer of a point is all those elements of G which fix that point. So if a group is acting without fixed points then the stabilizers are all trivial. So we will relax that condition here and say stabilizers need not be trivial but they have to be finite, okay. So the first condition is the stabilizer G sub Z, the set of all G belonging to G such that G of Z equal to Z is finite, okay. So this is a relaxation that you make. Instead of trivial stabilizer, which is the case of a fixed point free action, you make the stabilizer trivial. Then the second condition is with respect to that neighborhood that gave the proper discontinuous action. What was the earlier situation? The earlier situation was that apart from the identity element every other element of G has to completely move this neighborhood. Now what we do is we say that there is a neighborhood of the point which is completely fixed by every element in the stabilizer and completely displaced by every element outside the stabilizer, okay. So there exists an open subset, open neighborhood U of Z, so that you see G of U equal to U for all G in the stabilizer, and G of U intersection U is empty for all G outside the stabilizer. So there is one open neighborhood of the point which on which this finite group, namely the stabilizer, is acting, and if you take any element of the group outside the stabilizer that is going to push it away, okay. Now the beautiful thing is that this if you take the points, the set of all points, of course you know some groups may not have even a single point where they may act properly discontinuously in this relaxed sense, but it so happens that it happens for our PSL2, okay. So the general theory is, now given a group of Mobius transformations which acts properly discontinuously in this sense, okay, you can still go modulo that group, okay, and get something which is a more general case of a covering. It is called a ramified covering, okay, and you get what is called a ramified map of Riemann surfaces, okay. So what I want to tell you is that this is a relaxation of this I mean of the earlier definition of properly discontinuous action, and it is a very nice I mean weakening of the definition, but strong enough to give the quotient of U mod PSL2C. And so this will lead us to trying to understand various types of groups, namely discrete subgroups of Mobius transformations, then you know Kleinian groups, Fuchsian groups, okay. We are going to look at all that because these are the general kinds of groups which we would like to go modulo and try to get Riemann surfaces, okay. So we will do that in the forthcoming lectures.